In this video, I'll talk about their means. I'll talk about their fundamental structure, how they look like. I'll categorize those in terms of primary, secondary, tertiary amines, and also focus on some of the aromatic amines. And then in addition to that, I'll also talk about what type of intermolecular forces they make and their relative boiling points and the solubility in the water. So let's start out with just the basic structure of an amine. So a typical amine would have is actually a derivative of ammonia. So if I look at the simple structure of NH3, and if you want to go ahead and draw its loose star structure, it's just basically you have three hydrogens connected to the nitrogen, and you got a lone pair. So what we're really doing when we transforming this ammonia into an amine, we will be replacing these hydrogens with a carbon chain, or another way of saying with an R group. So suppose if I go ahead and have, instead of having three hydrogens, but rather I have only two hydrogens connected, and on one of the sides I have, let's say, a CH3 group. So that would be an amine now, and to be more specific, this would be in a primary amine. That's because I only replaced one of the hydrogens with an R group, and another way of saying I still have two more hydrogens connected onto that nitrogen there. If I want to go ahead and replace the second one as well, like, let me just go ahead and draw the skeleton here. Let's suppose I got this two carbon chain here, and now I want to replace the second hydrogen with another carbon set, and that could be different from what you originally have present on the other side, so it's completely okay. And then let's say I still have one hydrogen present on the bottom here, so this would be categorized as a secondary amine in that particular case. And then if I replace all the hydrogens with a carbon set, so like I can say, all right, I got CH3, CH2, nitrogen, let's say CH3 here, let's say another carbon, CH3 here, CH3 here. So those R groups could be very well different from one another, so they don't have to be necessarily the same. So in this particular case, I don't have any hydrogen connected to the nitrogen, but remember, you still have one lone pair on that nitrogen that typically you don't really show it for the most part, but it's kind of an automatic that it is there. So this would be categorized as a tertiary amine. So in addition to that, you can also have an aromatic amine. So in a typical aromatic amine, you have obviously an aromatic compound like in a benzene, and you can have an NH2 connected to it. So this is kind of a primary amine, but in addition to that, it's also going to be referred as an aromatic amine because the nitrogen is directly connected to the aromatic carbon here. And the common name for this aromatic amine where you just have a benzene ring and you got the NH2 is called an aniline. So let's try some of these questions here where you're just trying to figure out whether it's in a primary, secondary, tertiary, or aromatic. So starting from the first one, I can see on the left side I get an R group. I do have two hydrogens connected with that nitrogen, so this would categorize as in a primary amine. Let's look at the second one here. Again, I got two hydrogens connected to the nitrogen, and I only got one R group, so that would be still in a primary amine. And you want to probably pause the session here and do categorize these rest of them and then see if they matches with my answer here. So this next one I have is this nitrogen. I got one R group on the top here, and I got another R group on the bottom here. So that one is going to be having only one hydrogen, so that would be categorized as a secondary amine in this particular case. Moving downward here, I can see I got this nitrogen again. I got a methyl group on the left side, on the right side here. On the bottom, I have another methyl group. On the left side, I got a two carbon chain, which is an ethyl group. So it's surrounded by three R groups. There's no hydrogen on that nitrogen, so that means this is going to be a tertiary amine. And then I can also look at this next one where, okay, I got a CH3 here, I got another CH3 connected to the nitrogen, and on the bottom I got an isopropyl group. I'm missing a carbon and a hydrogen here, so I'm just going to go ahead and put in a hydrogen on that carbon there. So that would make it, again, a tertiary amine there. Looking at this next one here, it's in a ring, but remember it's not an aromatic ring. It does not have any of those double bonds conjugated with one another. So all I'm really seeing is a nitrogen that got two hydrogens and an R group, so that would be a primary amine. Coming down here, I got an isopropyl group, I got a methyl, I got an ethyl. So these three R groups connected to the nitrogen, that would make it a tertiary amine. Now this next one is indeed I got a nitrogen directly connected to the aromatic ring. So I can say this is going to be an aromatic amine in this particular case. Now, you call this an aromatic amine only if you have a nitrogen directly connected to the aromatic ring, or you can say the benzene ring in this particular case. Like in this next example, you see that you do have an aromatic here, but when you look at that nitrogen, it's not actually directly connected to the ring, but rather there is a carbon in between those. So this would be just considered like in a typical R group. We're not going to be calling this an aromatic amine, but just regularly primary amine in this particular case. Now, the previous one, you could also call that a primary amine as well, but to be more specific, you would also categorize this as an aromatic amine because the nitrogen is directly connected to the ring in this particular case. Okay, so this is how you're going to be categorizing those. So let's look at some of its boiling point, relative boiling points in the solubility. So I'm just going to be comparing um, these guys right there that I got in the pair. I'll talk about what their possible boiling points or relative boiling points would be, like which one would be higher and lower, and then what their solubility is going to be in the water. So obviously, um, to define what the boiling points and the solubilities in water are going to be, you're going to have to look at to what type of intramolecular forces these guys are making. So I'm gonna say if something is going to be making an hydrogen bond. So let's say hydrogen bond. I'm going to be writing A for that, and then a dipole dipole would be a B for that, so that I don't have to rewrite the whole thing again and again. And if something is making dispersion forces, that would be an a C. Okay, so remember the dispersion forces is going to be in every single one regardless what we are really looking at. So I can say, okay, this guy is making dispersion forces and so is this guy. Now when I'm looking at what other intermolecular forces this can make with itself, well, I do see in a nitrogen directly connected with these two hydrogens. And remember, the criteria for the hydrogen bond is the hydrogen must be connected with either fluorine, an oxygen, or a nitrogen. So that means this actually can make hydrogen bonds. So I got A in there. And then I also see there is a polar bond that's going to be between the carbon and the nitrogen. So because of that polar bond, it will be able to make the dipole-dipole as well. So I will be saying A, B, and C, all three intermolecular forces are going to be made on this left molecule. When I'm looking at the right one here, I don't really have any hydrogen directly connected to the nitrogen. So your hydrogen bonds are out of the question here. But I do see these carbons and nitrogens kind of connected. So as a result, they would be making these dipole-dipole interactions. So I got a dipole-dipole and a dispersion for the second one. Okay, so if the molecule's molar mass is relatively similar, like these guys, they will have, slightly differences in their molar masses, but there's not going to be a big difference. So I'm just going to be focusing on what type of intermolecular forces these guys are making. So hydrogen bonds, remember, is going to be the strongest out of all the intermolecular forces. So if something is making hydrogen bonds and the other guy is not making hydrogen bonds, that means it would have a higher boiling point. So this one would have higher boiling point. And then also, when it comes down to the water solubility, you want to make sure you have as much as polarity in the hydrogen bond there. So, I mean, I can see the mean on the right side is a little bit more. It's also polar because it can make dipole dipoles, but it cannot really make hydrogen bonds. So as a result, I want to go ahead and say we will have a better solubility of this left amine in the water. So I can say this is going to be more soluble in water. Now, exactly how much, that's not really the question. We're just trying to qualitatively compare these two with one another. Let's look at this next one here. So suppose I got The left one, all I really have is just the carbon-carbon bonds and the carbon-hydrogen bonds. So this is only going to be making dispersion forces. So I'll say C. And then on the right side, I do have an NH there. I got a carbon nitrogen there, and I got obviously the dipole dispersion forces because I got carbon-carbon bonds and carbon hydrogen bonds. So this would be making all three types of intermolecular forces. So as a result, this would have higher boiling point, and this would also be more soluble in water or higher solubility in water. You can also say that. Let's look at this next one here. Okay, so on the next one, I can see it's in a tertiary amine, and I got the dipole-dipole in there because of this nitrogen carbon bond, and certainly I'm going to have dispersion forces. But on the right one, I only see carbon-carbons and carbon-hydrogens, so that means only dispersion forces. So just because the one on the left side is making dipole-dipole interactions as well, it would have relatively higher boiling point, and it would have higher solubility in water as well. So just because something has a higher boiling point, that does not necessarily mean it's going to have a higher solubility in water. Uh, the higher solubility in water is typically comes from what's really going to be the polarity overall of the molecule. And if you have too much of non-polarity going on in the molecule, it would be less soluble in water. Let's look at this next one here. I got pretty much the same number of carbons, but I got an amine group and I got an OH group. So it's typically it's in a different types of function group in there. So on the left one, it will be making all three intermolecular forces, and so is the right one because also an OH you can make an hydrogen bond and it is going to be polar, so you can also make dipole-dipole interactions. Now, when it comes down to looking at the in this particular scenario where I really don't have any differences among the structures in terms of how many carbon chains I got, and also in terms of what types of intermolecular forces being made, then you may have to look at the strength of these intermolecular forces. So it turns out when you have a hydrogen bond that's made when there is an OH versus when there is an NH, the OH hydrogen bond is actually a lot stronger than the NH. So as a result, it would have a higher solubility and the higher boiling point. So I can say this, I can write down here, it's going to have stronger hydrogen bond because oxygen is more electronegative than the nitrogen. So it's got stronger hydrogen bond. So as a result, it's going to have a higher boiling point. And based on that analogy, I could also say this is going to have a higher solubility because it just have a stronger intermolecular force or hydrogen bonds to be more specific. Let's look at this next one here. So again, on this next one, I got the NH2. It's in a primary amine. That's in a primary amine on the right side as well. So this will be making all three types of intermolecular forces. The same story with the right one. It would be making all three types of intermolecular forces. Now, the difference that really got in there is actually the chain. So on the left one, you have like six-membered ring here. On the right one, it's only got two carbons. So whenever you run into that scenario where you have the same type of intermolecular forces being made, then you want to look at the size of the molecule overall, because a bigger size means you can make more dispersion forces. So you can have more dispersion forces on the left side, and everything else is kind of the same. So higher the surface area, more the dispersion forces, that means it's going to have a higher boiling point. So this one would have higher boiling point as a result. But when you look at the one on the right side, I do have the dispersion forces in there, but the amount of dispersion forces the one on the right side is making is going to be a lot less than what we were making on the left side. And remember, when it comes down to solubility, we want to make sure we have as less dispersion forces as possible because the dispersion is something where that the water doesn't really like because of the differences in the polarities. So since you have less dispersion forces or less non-polarity on the molecule that's on the right side, it would have higher solubility in the water. So typically, if you have, I would say maybe up to 5 carbons, 5 to 6 carbons roughly. If you have up to 5 carbons, you can dissolve the amine and even the alcohols in water. But as soon as it starts going over 5, then they almost becomes insoluble in water, even though they would have hydrogen bonds in there. That's because once it starts going over 5 carbons, the hydrophobicity or the non-polarity starts taking the dominance over these small polar sites in that particular case. So remember, the border is kind of a 5 to 6 carbons for most of the cases. Whenever there is a group that can make an hydrogen bonds versus just a 5 6 carbons that's just gonna have an hydrophobic nature. But if you have a negative charge, like, or a positive charge, as a matter of fact, it doesn't really matter, then it can handle up to like 20 to 25 carbons. So like I can have, let's say, an oxygen with a negative charge, and it can have like, let's say, 20 carbons connected to it, and it will still be dissolved in water. That's just because the charge, whether it's in a cation or anion, it just increases the solubility in the water dramatically.